Okay, very good afternoon. So for these sessions, I'd like to talk about the next mature response that we discussed in the lecture, which is a viscoelastic mature response, and how we can develop a constraint models or maturity model for viscoelastic mature response. So this is the lecture that we did not manage to do it in real-time mode. So that is why I simply recorded this lecture for your reference, noting that lecture 6 will not be included in the final exams, but I will strongly suggest you to continue listening and then following this lecture 6, all right? Okay, so we are focusing on the viscoelastic mature response, and this is a class of mature response commonly observed in many classes of polymeric materials. So if we look at the list of lectures in this class, so we have done from lecture 1 all the way until lecture 5. So today we are going to discuss about lecture 6. Again, lecture 6 will not be included in the final exam. Your final exam will only be focusing on lecture 5 all the way until, lecture 1 all the way until lecture 5. Okay, in this brief lecture, I would like to split it into two parts. The first part will focus mainly on the basic concept of viscoelasticity. So the idea is to give you a background, fundamentals on what viscoelasticity is. And then secondly, of course, we are going to talk about how we can develop mathematical equations to describe the stress-strain characteristic of a viscoelastic material. So let's have a look now to the first part. Okay, let me start by looking at what happened in industry, specifically looking at a phenomenon called as creep. Okay, if you look at in a lot of process industry, we use a lot of pipe system. Okay, and then if you notice in the pipe systems, they can be very complex, ranging from straight pipe to pipes which contain a lot of bands depending on the needs and the process in industry. If we look at the example here of portions of the pipe systems, especially focusing on the portions of the pipes between these two supports, between these two brackets, we know that these portions will undergo sag or deflections because of the pipe self-weight. This is a natural situation, okay? And then since these portions we can consider the self-weight is constant, so as if it is subjected to constant stress because of self-weight. So this on the right is the illustration on how the stress is constant over time because the weight that we consider is constant over time. If the materials of the pipe is made, if the pipe is made of materials without viscoelastic characteristic, then the resulting sag, the resulting deflections will be constant. And you know how to estimate the deflections from mechanics of materials that you have learned. Okay. However, if the materials of the pipe is viscoelastic, then what will happen is that the amount of sag, the amount of deflections will continuously increase with time, which means that even though we impose constant stress, but the resulting strain will change, will increase over time. And this is a characteristic shown by a viscoelastic materials. And the fact that the strain increases at constant stress is a phenomenon which is called as creep. Okay, so another typical example is that this pipe will be used to transfer, for instance, fluid, gas, for instance, and the gas has internal pressure. You have learned also in mechanics of materials that whenever a pipe or cylinder is subjected to internal pressure, then it will generate stresses. For instance, the stresses will be radial stress, hoop stress, and longitudinal stress. Okay, so this stress will generate deformation, strain in the pipe. So what happens is that if the pipe is made of purely elastic materials, then the resulting deformation, for instance, decrease in the thickness of the pipe, will be constant because the pressure is constant, the stress is constant. We use purely elastic materials, then the resulting decrease in thickness will remain constant over time. However, if the pipe again is made of materials which show significant viscoelastic response, what will happen is that the pipe will continuously decreases in thickness. So this continuous change in the deformation in the strain at constant stress is another example of creep phenomenon in industry. So when we design a pipe made of viscoelastic materials, as mechanical engineer, we need to make sure that the resulting deformations, the resulting change of thickness, for instance, remains within allowable ranges. Another example that I'd like to highlight in industry is a phenomenon called as relaxations. If we look at in the sealing system, we use a lot of rubber materials. Rubber used to seal certain regions so that it will not mix with other regions. Again, as the name implies, it is to seal. So when we put the seal, basically we press it so that the seal will deform at constant deformations. So unlike to what happened before, in these applications, we deform the seal at constant amount of deformations. If the seal was made of purely elastic materials, what happened is that the fact that we deform it constantly will generate also constant stress. However, if the sealing systems is made of viscoelastic materials, what will happen is that even though we impose constant strain as illustrated in the graph here, the resulting stress will decrease over time. And this is a phenomenon called as relaxations. Stress will decrease in rubber seal after installment, which later on may lead to leak in the systems. Okay, so what happened is that over time, basically mature stiffness change, mature stiffness decreases. So this is the second example where considering a viscoelastic response is crucial when you design a component involving viscoelastic materials. So you need to make sure you take that into considerations in the design or in the stress analysis. So if we look at the basic definitions of viscoelasticity, basically it is the time or rate-dependent behavior where the stress response depends on both strain and time or strain rate. Okay, both strain and time or strain and strain rate, it's the same, basically between time and strain rate. So viscoelastic materials displays all the intermediate range of properties between an elastic solid and a viscous liquid. So it is sort of like combinations between the elastic solid and viscous liquid. The typical characteristic of viscoelastic material is that it may change whether it becomes closer as an elastic solid or closer to viscous liquid depending on temperature or strain rate. If you bring the viscoelastic materials to low temperature or high strain rate, or you load it at high loading rate, high strain rate, so what happens is that the response will be tend to move and close to elastic solid. However, if you bring the viscoelastic materials to a sufficiently high temperature or equivalently loaded at sufficiently low strain rate, then the behavior will be closer to a viscous liquid. Okay, so the mechanical response of viscoelastic materials depend on temperature and how fast you load the materials. And then in order for us to check whether a materials possess a viscoelastic response or not, then in the laboratory, we can do two simple cases of tests. The first one is relaxation test, and second one is creep test. And polymeric materials are a typical example of viscoelastic material. So how do we conduct the tests? Okay. First, about the relaxation test. So what happened is that imagines that we have this bar, and this bar is subjected either to constant strain or constant stress. So constant strain or constant stress. If the materials is purely elastic, what happened is that the stress generated in the materials will remain constant. Or in the second case, when we impose constant stress, then the resulting strain will also be constant over time. However, if the materials of this bar is viscoelastic, so what will happen is that if we impose constant strain, the stress will relax, will decrease. While in the case of creep test, the second one here, when we impose constant strain, when we impose constant stress, what happens is that the strain will increase over time if the material is viscoelastic. So you see the difference between elastic materials and viscoelastic materials. Constant strain lead to constant stress in elastic material. Constant stress lead to constant strain for elastic materials. But for viscoelastic materials, constant strain leads to stress which will decrease over time, while for constant stress, then viscoelastic materials will provide a response whereby the resulting strain will increase over time. So the first case here is called as relaxation test. The second case here is called as creep test. This is how we do it. Again, I repeat, if we want to do relaxation test, then we pull it here, apply constant strain. For instance, we keep the materials at 10% strain and see what happened to the stress. If the resulting stress that you observe is constant, then your materials is simply elastic. However, if it decreases over time, then your materials is viscoelastic. And similarly, for the creep test, this time you impose constant stress, for instance, 10 megapascal, you observe what happened to the strain. If the strain is also constant, then your materials is elastic. However, if your strain change, evolve, and increases with time, then you're dealing with a viscoelastic materials. Okay. Now, if you are dealing with viscoelastic materials, what can we obtain from the relaxation test and creep test here? From the relaxation test, we can obtain a property called as relaxation modulus, which is sigma over strain, epsilon. The sigma here evolved with time. That is why it is a function of time. From the creep test, we can then extract a property called as creep modulus. Okay, also defined as a ratio between stress and strain. The only difference is that the stress this time is a constant, while the strain is evolving with times. So this is the notations commonly used for relaxation modulus, ER, a function of T, which means that the properties evolve as a function of time. And this is the characteristic of viscoelastic materials. Similarly, creep modulus, also a function of time. So in this example, it is noted by EC, but very often also it is noted as D or creep modulus. Okay. All right, so just quickly from physical standpoint, what happens when relaxations occur in a polymer is actually under constant strain, the stress decreases with time. And then stress relaxations allows the polymer to reach lower energy states spontaneously, of course, providing that sufficient activation energy for the process to occur. So this is what happened. And then stress relaxation is temperature dependent. So depends on the temperature. And then stress relaxation is due to viscous flow in the material's internal structure. So you can imagine that the polymeric chain slowly sliding by each other by breaking and reforming of secondary bonding between the chains. And then also by mechanical untangling and recoiling of molecular chains. So this is quickly the physical mechanisms of relaxations in polymer. And then for creep, in industry, the creep of polymeric materials is measured by the creep modulus, defined by the ratio between initial applied stress to the creep strain. And then high creep strain high creep modulus implies a low creep rate. Okay, so high creep modulus means that high resistance to creep. And then bulky side group and strong intermolecular forces reduces the creep rate. And then we can increase the creep modulus in polymer by, for instance, adding reinforcement fiber, such as glass fiber, to increase their creep modulus at the same time to reduce their creep rates. All right, so this is very quick for the basic concept of viscoelasticity. Again, viscoelasticity is response of materials which depend on temperature and loading rate or strain rate, which means that the properties that you obtain in the materials will depend highly on which temperature you're conducting the test and how fast you load the materials. Okay, so it adds a little bit complexity as compared to a simple elastic materials. Okay, so the next one is about considering model, the mathematical model or materials model to describe the response that we have seen before. We can go for physical approach and also phenomenological approach, similar like in linear elastic or nonlinear elastic material response. However, in this lecture 6, for simplicity, we will only focus on phenomenological approach. We are not going to look at physical approach because it is a little bit more complex and then not within the scope of this lecture. Okay, so I will just give you example of phenomenological approach to example more precisely, which is direct extensions of linear elastic model, and then secondly is Boltzmann superposition principle. There are still a number of other models, for instance, integral model, rheological models available, but not discussed in this lecture. So I will just simply focus on these two simple materials model. So let's have a look one by one. The first one is model 1, which is simply extensions of linear elastic materials model. So I show again this table from linear elastic material response, where we highlight how actually applying the stress, normal stresses or shear stress would generate strains. So for instance here, if I apply sigma xx, then this is the resulting strain along normal strain along x, normal strain along y, and normal strain along z, and so on and so forth. For shear stress, for instance, if I apply shear stress along the plane xz, then it will generate only the shear strain along that particular plane, which is xz. The rest are 0. Okay, so we have seen this for linear elastic material response. So the first material models that we can use to describe viscoelasticity, we can use exactly the same thing here. Okay, for stress-strain relations. The only difference is that the properties will depend on time. So we see the property here, which is E, elastic modulus, and then also Poisson ratio. For elastic materials, elastic modulus is constant. Poisson ratio is constant. While for viscoelastic materials, both will depend on time. So the easiest way, the most straightforward way to get the materials model for viscoelastic response is by simply extending the linear elastic materials model for viscoelasticity. So for viscoelasticity, the above parameters depend on time or strain rate. Okay, let's have a look on this example how to use it. A very simple one. So we have, for instance, a bar of polypropylene with the length of 200 mm and cross sections of 25 times 3 mm. It is subjected to a constant tensile load of 250 newtons acting along its length. 100 seconds after the load was applied, the length is measured and is found to have increased by 0.5 mm. Determine the 100-second tensile creep compliance. So creep compliance is the opposite of creep modulus. So creep modulus is sigma over E, where sigma is constant and creep compliance is, I will repeat again, creep compliance is the opposite of creep modulus, 1 over creep modulus. we know that crypt modulus is sigma over epsilon, where sigma is constant and epsilon evolve with time. So crypt compliance simply epsilon over sigma, inverse. Okay, so epsilon depends on time. So the question is determine 100 seconds tensile crypt compliance. So the first thing that we need to do, of course, is to calculate the stress. The crypt stress is constant. So F over A as usual, and we find out that it is 3.33 megapascal. It's a constant, all right? And then the next thing we do is that we know the resulting strain at, if I go back, at 100 seconds. Okay, so we can calculate the crypt strain at 100 seconds. In the same way, it is delta L over L0, but the delta L at 100 seconds. And we found the value, it is 2.5 times 10 minus 3. This is the crypt strain at 100 seconds. So the tensile crypt compliance also at 100 seconds is simply the strain, the crypt strain over sigma. So the crypt strain is, we have here, and then sigma is constant 3.33, and then we have here the crypt compliance is 0.75 gigapascal minus 1. Gigapascal minus 1 means that it is 1 over gigapascal. Okay, I hope it is clear. We can have a look to the second example also for a simple extensions. So we use exactly the same materials models as linear elasticity. We simply change the properties to become dependent on time or strain rate. Okay. So let's have a look at this example. A spherical vessel is molded from a polymer whose 1 month tensile crypt compliance is 2 gigapascal minus 1. The vessel is soft diameter 400 millimeter and wall thickness 5 millimeter. A constant internal pressure is applied to the vessel, giving rise to a tensile stress 1.6 megapascal, acting uniformly in all directions in the plane of the vessel wall. By assuming the polymer to have a constant Poisson ratio of 0.41, determine the change in diameter and change in wall thickness after 1 month of pressurizations. And then the equations that you can find from your mechanics of materials, how a cylindrical vessel, or this one is spherical vessel, is subjected to internal pressure. It will generate sigma tangential, which is PR over 2T, while the radial stress, you can put either minus P or 0, depend on your choice. Either way, it will lead to more or less similar result. Okay, noting that because of the symmetrical shape of this spherical vessel, if we take out one element of the wall, so either the stress in these directions or these directions are all basically tangential directions, and then it is given by PR over 2T. P is internal pressure, R is the radius, and then T is thickness. Okay, now, so looking at these elements, so this is sigma xx 1.6, sigma yy also 1.6. It is given in the example directly. So we can make use of linear elasticity theory here. So the materials is subjected only sigma yy and sigma xx, and then the sigma zz, which is the radial stress, I take 0. You can take minus P, but I prefer 0 to make it simple. Okay, if you do and you choose by using minus P, the result will not be much different. Okay. So which means that I only have sigma xx, sigma yy, sigma zz is equal to 0, the radial stress. Okay, and then there is no shear stresses, so I don't need to put it here. And the resulting strain are simply sigma xx over E. I put it D, where D is the crypt compliance. Okay, 1 over E. Okay. Similarly, all here put exactly the same thing, except that I just put it in the terms of D because the information that I have is crypt compliance. Okay. So once I put everything, then what I do is that simply combine all, because we know that sigma xx equal to sigma yy equal to sigma, while sigma zz equal to 0. Sum up all here, this is epsilon xx, the resulting epsilon yy, and the resulting epsilon zz. Okay. And then if we insert all the value here, d, and then also sigma, what happened is that this is the value of epsilon xx that we obtain after 1 month. This is the value of epsilon yy after 1 month, and then this is epsilon zz after 1 month. Okay. So looking at calculate further the change in diameter, it is delta d is simply initial diameter times epsilon xx or epsilon yy. So it is, we found it is 0.756 mm positive, which means that the diameter will increase, while the change in the thickness can be obtained from epsilon zz. This is the radial strain. And delta t is simply t0 times epsilon zz, and then we have it is minus 1.31 times 10 to the power of minus 2 millimeter. We have a decrease in the thickness. So this is a simple example on how we do the stress analysis for viscoelastic materials by simply using the materials model for linear elastic materials, changing uniquely the value of the properties to become dependent on time. Okay, so I hope this is clear. So the second one is slightly new, okay, for you, and this is called as Boltzmann superposition principle. Again, I will simply briefly discuss about these models, and you can read in a lot of books about viscoelastic models on Boltzmann superposition principle for further information. So here it's the same. Mr. Boltzmann work in thermodynamics, entropy, Boltzmann's equations, okay, Boltzmann constant. So it is an Austrian physicist who proposed the following as a basic principle to describe the response of a viscoelastic materials. I will just simply read it, and then we will see how it's translated into equations. Okay. So according to this principle, under arbitrary loading, the viscoelastic material response is a function of the entire past loading history of the material. Each loading step makes an independent contribution to the final response so that the total response can be obtained by the additions of all the contributions. What does it mean? Let's have a look here. Imagine that I have a viscoelastic materials and it is subjected to constant stress by the amount of sigma 0. So this is how the stress evolves over time. It is constant sigma 0. Because the materials is viscoelastic, of course, the resulting strain will evolve over time. And this is, for instance, the example of how the strain will generate in the materials over time. And this will be given by epsilon 0t equal to sigma 0 times dt. Again, d is creep compliance. It is 1 over elastic modulus. Okay. All right. So this is what happened. Now, imagine that instead of applying stress from initial time 0, I apply it at certain given time t1. I start to impose it at t1. And then the amount is multiple times than sigma 0, for instance, k sigma 0. So what happened is that, of course, the strain will start to develop at t1, not at t equal to 0. It will start here. And what happened is that the response here will be simply the multiple of the response that I have in the red one here. So it is equal to sigma 1 times d. Sigma 1 is multiple of sigma 0. Something which is, you have to be careful here is that this is the creep compliance functions of time of t minus t1. Why minus t1? Because the applied stress only start at time t1. In the previous example here, we simply put d as a function of t because the load start at t equal to 0. So it is equivalent with d t minus 0. Okay. All right. This is what happened. What if the materials is subjected to this kind of loading, which is basically combinations of this one? For instance, start with the red one. After that, apply the blue one. And this is what happened here. So this is the first one that we seen before, and this one is the second one. And the response of materials will be, the first one is here, which is because of sigma 0. And then starting from T1, it becomes multiple because of the application of sigma 1. The question is, what is the value of this epsilon T? All right, so now here we look back on the loading. This is sigma 0. At the time T1, the sigma, we apply multiple of sigma 0. For instance, K times sigma 0. And let's say that this value, we call it delta sigma 0. And delta sigma 0 is actually sigma 0. While the rest here, if we call it delta sigma 1, then delta sigma 1 will be sigma 1 minus sigma 0. All right. So how do we describe this epsilon T as a function of something that we see in the previous slide here? Okay, according to Boltzmann's, it has to be superposition, add up, the sum. Okay, so we simply need to sum up the response because of sigma, the applications of this one, the first loading, which is the amount is delta sigma 0, and then the second increment, which is delta sigma 1. It is the increment that we have to consider. Okay, so according to Boltzmann's superposition principle, for a linear viscoelastic polymers, we have epsilon T is, what is the amount of increment that we have in the first loading? It is delta sigma 0 times D at times T minus T0, where T0 is 0, which is this one, because sigma 0 start at T equal to 0. Plus the second increment here, which is delta sigma 1 times the creep compliance, and then this loading start at T1. So we have to put the creep compliance at times T minus T1. This is how we write it. Okay. If we have this kind of loading, what should we do? The load start at T1, and then this is the delta sigma 1, and then at T2 we apply delta sigma 2, and then at T3 we add again by delta sigma 3. So this is increment. So what we consider is increments. This is the illustrations of the response of the materials. And then mathematically, according to Boltzmann superposition principle, we simply sum up the three loading contributions. Okay, so this is the first contributions with the increments of delta sigma 1, this one. And then the load start at T equal to T1, plus the second increment of load, which is delta sigma 2. Be careful, it has to be the increment, not the value itself. Okay, so D, which start at T equal to T2, and then plus the third increment of the stress, which is delta sigma 3, which started at T minus T3. So this is how we do the Boltzmann superposition principle for materials under a certain loading. So as you can see here, if the material is subjected to continuous increasing stress, so what will happen is that the distance between T1 and T2 become very small and becomes continuous. As you can see, the sum of this becomes integral. Okay, so this is another form of representing Boltzmann superposition principle. I'll give an example to close. Okay, how to use it, just so that you have idea how to use Boltzmann superposition principle. Let's say that I have a polypropylene which is subjected to the following time sequence of tensile stress at 35 degrees Celsius. At times less than 0, which means that in the history before any applications, the stress is 0. So nothing happened before. Okay, and then between 0 to 1000 seconds, the polypropylene is subjected to 1 megapascal stress. And then from 1000 to 2000 seconds, it becomes 1.5 megapascal. And then starting from 2000, we remove the stress. So the stress is 0. So using the Boltzmann superposition principle, determine the resulting strain at times T equal to 1500 seconds and T equal to 2500 seconds if the tensile creep compliance of the polymer is found to have this value, which is dt equal to 1.2 times 10 to the power of minus 3 times t to the power of 0.1 megapascal minus 1. Okay, how to answer these questions? So we have the loading sequence as given here. So the first thing that we have to do is sketch the loading sequence. Okay, so here is t0 equal to 0. So before that, it is 0. And then from 0 to 1000 second, we apply stress by the amount of 1 megapascal. So what happened is that if I call this as delta sigma 0, then delta sigma 0 is 1 megapascal. And then starting from t equal to 1000 until 2000, the stress become 1.5 megapascal. So the increments, which I call as delta sigma 1, is 0.5, obviously. And it happens until 2000 second. After 2000 second, the stress is removed, becomes 0. So is continuously becomes 0. So the delta increment that we have, delta sigma 2, is minus 1.5. Okay. So this is t0 equal to 0, t1 equal to 1000, t2 equal to 2000. And then the question is, what will be the strain when t equal to 1500 and when t equal to 2500? So obviously, when we look at times t 1500, it involves only two loading increments. So we only need to sum two loading increments, which is because of delta sigma 0 and delta sigma 1. If we want to know the resulting strain at t 2500, then it involves three loading increments, which is delta sigma 0, delta sigma 1, and delta sigma 2. Okay, noting that the stress is 0 here. So if we were to deal with purely elastic materials, obviously the resulting strain will be 0. But you will see that for the case of viscoelastic materials, it will not be 0. First, let's have a look for 1500 second. It involves two increments, as I mentioned. So it is delta sigma 0 times d t minus t0. This is t0 plus delta sigma 1 d t minus t1. This is t1. So we simply need to put delta d0 is 1. The creep compliance, we have it before, and then we replace the value of functions t by t, which is 1500, minus t0, which is 0. So this is t 1500, we insert here. Minus 0, 0 is t0. Plus the second increment, the same thing, t minus t1. T is 1500, the times that we want to evaluate, minus 1000, 1000 because the second increment starts at 1000. So when we calculate, we have this is the value of strain at 1500 second. What happens at t 2500? We simply need to add the third increments, noting that we replace here t by 2500 instead of 1500 before, and then if we do that, we will find that it is equal to 0.52 times 10 to the power of minus 3. Okay, so as you can see here, the stress is removed at 2000 seconds. When we investigate 500 seconds later at 2500 seconds, the strain is still not 0 yet. So which means that after 500 seconds, after the stress is removed, the strain is not 0 yet. It takes some time. Okay, you need to wait even longer to make it the strain equal to 0. All right. So this is an example of how the response, the typical response of viscoelastic materials, it depends on time. Okay. All right. So I hope this is clear. It is very short, but at least hopefully it gives you more idea about what viscoelastic response is. So we have discussed basic concept of viscoelasticity. We have discussed model for viscoelasticity. Again, this is served as additional knowledge for you, and then it will not be included in your final exams. All right? Okay, thank you very much.